Hi, back again for parallel circuits this time. So instead of series circuits where it's one right after the other, now we are moving to a parallel circuit where you have different branches that you can go through. So here we go. Here's our battery again, plus minus. And here's one path with a bulb in it. Here's another path with a bulb in it. So that's our parallel circuit. Now you actually have experienced parallel circuits as well. The series circuit is kind of like the line at the airport where you have to go get your ID checked, which is a resistor, and then you go through and you have to go through and get your baggage checked, which is another resistor. Parallel circuits are fascinating. What we saw with the equation for the total resistance is that you add more parallel circuits and the total resistance goes down somehow, which is really weird if you think about it. Because we're adding resistance to the circuit, but the total resistance is going down? Okay, how does that work? Well, parallel circuits are like the checkout lanes at a grocery store or a Target or whatever. So it's Christmas time, you're shopping, everybody else in the world is shopping, and there's a huge backup of people trying to get out of the store. So right now, the flow of people, the current is very small. What does the manager do? The manager opens up more checkout lanes. So now we've got another lane open, another lane open. And what happens to the total flow of people going through the store? Well, the total flow goes up. You get people out the store more quickly. So parallel, even though you're adding resistors, that's not the important part. It's that you're adding branches or loops. You're adding paths. So parallel, every time you add another branch or loop, you're actually reducing the total resistance of the circuit and allowing more charge to flow or more people to flow. So that's a parallel circuit. Total resistance is smaller than an individual resistor or resistors in series. So we've got this as our rule for the resistance, and then we still have Ohm's law. Still got that. We've got voltage equals the current times the resistance. And as I said with the series, there's two forms of this. So we have the voltage across the battery. We have the voltage across R1. We've got the voltage across R2. And again, voltage is always across. But now we also have current. So we've got some current coming out of the battery. We've got the current going through R1. And we've got, oh boy, the current going through R2. Those are all the things that we can calculate, add, measure. But here, okay, voltage across the battery. This is going to be similar to what we had before. The voltage across the battery is the current through the battery times the total resistance. Or we could have the voltage across one resistor is the current through that resistor times that individual resistance. So those are important to keep in mind. You can't say I'm going to use the voltage across the battery and the current through resistor 1 because they're not the same thing. You have to keep it all consistent. So what's true about voltage and resistance in a parallel circuit? Well, let's look at the voltage first here. So the voltage is the amount of push given to charges as we go through the circuit, and it's always across. Remember, voltage is always measured across. So if the battery is providing a certain amount of oomph, saying, I'm going to push these charges out, well, those charges say, okay, I'm going to go here, whee! And in this loop, the amount of oomph that the battery was giving to the charges is the same as the amount of oomph that gets used up pushing those charges through the resistor. And if you think about this loop, the big loop, well, battery's got to push some there and it's going to just get all used up there. So the nice thing about parallel circuits is that the voltage is the same across all the different loops. So the voltage is the same in parallel circuits. This doesn't have a nice, easy to remember acronym like series does, but hey. So the voltage is the same. Whatever voltage we have here to here is the same here to here and same here to here. And if you think about it, well, I'm measuring the same 2 points, aren't I? All of these are effectively the same point. All of these are the same point. So, yeah, the voltage here to here should be the same here to here, here to here. It doesn't matter where I would put a wire or a measuring device. This is all effectively the same. This is all effectively the same. Voltage is the same. Now, what's true about the current? So the current in parallel. All right, so the battery's kicking out some current. And again, current is flow of things, actual things, charges. So we kick out a whole bunch of current. These charges go boop, 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 and get to here. So what's going to happen to the charges when we get to that point? Some of the charges are coming in from the battery. So we got this pile of charges coming in, huge amount there. Some of those charges are going to end up going down this branch, but some of those charges are going to go this branch. So with the current in a parallel circuit, we end up with kind of the same rule as we had for voltage in series circuits. The current that comes out of the battery had better be the current going through resistor 1 plus the current going through resistor 2. Because again, we're talking about physical movement of things here. If 100 electrons came into this junction, 100 better come out. Now with the different resistors is the amount of current that's going to go through those 2 branches, those loops, going to be the same. So if this was a 10 ohm resistor, this was a 10 ohm resistor, well, they're equally difficult, so I would expect, yeah, the amount of charge to be going through each of those branches should be the same. But if one of these is more resistant, so in this case, I don't know, let's say I used 120 last time. So if this is 100 ohms, and this is 20 ohms, so charges come here and say, oh man, this is a really difficult path. This is a really easy path. Most of those charges are going to get shoved through the easier path. Not all of them. Some of them are still going to go through here, but there's going to be a lot more of the charge coming through the easier one. So less resistance, more current. So for the same voltage, if we reduce the resistance, the current needs to go up to balance it out. So those are our 2 rules for parallel circuits. The voltage is the same, and the current is going to have to add up. And then we've got our rule for calculating total resistance. We've got our Ohm's law, which has 2 different forms. Now we can do the same thing as we did. So let's do an example of a problem here. So if I've got my basic parallel circuit, here's R2, here's R1, here's my battery with a voltage across it. Let's see. Oh, I'll do the second one again, do my middle one. So I'm going to have the same set of variables. I can have resistor 1, I can have resistor 2, the voltage across the battery, voltage across R1, voltage across R2, current through the battery, current R1, current R2. Whew, that's a lot. So how do we figure this out? All right, what am I going to give? In this case, I was given that R2 was 9 ohms, and VR1 is 18 volts. And the current through the battery is 2.5 amps. All right, so that's what I'm given. I want to fill in all the others. Okay, so just like with series circuits, I can use my rules here. Voltage is the same, currents add, to kind of give me little reminders. The voltages have to be all the same. So all 3 voltages are the same in parallel, whereas the current through the battery is going to be the 2 currents added together. So now I look at that and say 2 blanks, not going to be helpful. This one's really easy. 18 volts everywhere. Okay, 18 volts, 18 volts. Resistor 1, current through resistor 1, current through resistor 2. All right, so now I have to figure out which one's going to be easiest to solve. Well, let's go back to Ohm's law. What do I know about resistor 1? Oh man, I don't know much about resistor 1, do I? Because with Ohm's law, in order to figure out R1, I need to know the voltage and the current. I know the voltage, I don't know the current. Okay, so don't see a way to get that right now. Maybe I can get one of these. Well, IR1 has the same problem. I'm missing the resistor. Maybe I can figure out what the current through resistor 2 is. So, all right, if I do this formula, the voltage for resistor 2 is the current through resistor 2 times resistor 2. Do I know these? VR2, yep, is 18. Do I know the current through resistor 2? Well, that's what I'm looking for. Times the resistance 2. Right. Ha! I can do it. So I now know that the current through resistor 2 must be 2 amps. That was pretty easy. Okay, so now I know current through resistor 2 is 2 amps. And now, got it. 2.5 amps equals something plus 2 amps. I think I can do that. The current through resistor 1 has to be half an amp. And at this point, I can go back here and get the last thing. So if I do VR1 equals IR1 times R1, okay, VR1, 18, equals IR1, 1/2 times R1. And 18 divided by 1/2 is 18 times 2. R1 is going to be 36 ohms. And so now I can put that in here. 36 ohms. Oh boy. Okay, so have I done it all? Well, I've answered everything. Now there is, again, a way you can double check. So we didn't use this idea here. If you want to double check your math, you can use this idea and see if you get the same answer. So we should get 1 over our total. Oh, what's that going to do? Well, okay, is 1 over 36 plus 1 over 9. So how can I use that to figure out anything? So you might say, that doesn't help at all. Great, I know our total. Well, we can figure out what our total is, and that's right here. So if we know our total, we can verify that we get the same our total with VB and IB. So I'm running out of space, sorry. There's 1, there's 2. VB equals I battery times our total. All right, VB was 18 equals I battery 2.5. Oh man, times our total. So with this, did I have my math here? Oh, I didn't even figure it out. I didn't do the important thing and check my own math. 18 divided by 2.5. Oh. Here you're going to see me scribble. 18 over 2.5 is 18 over 5 halves, which is 18 times 2 over 5. That's not a nice number. 36 over 5, that's 35 over 5 plus 1 over 5. So that's 5.2. Okay, 36 fifths. All right, so from this method we get our total is 36 fifths. We'd better get 36 fifths with this method. So, oh man, 1 over our total is 1 over 36 plus 1 over 9. 36 is a common denominator. So 1 over 36 plus 1/9 is 4 36ths. So 1 over our total is 5 over 36. It's working. So now again, you can flip both sides. You don't have to cross multiply when you can just flip them both over. Is 36 fifths. Ta-da! Okay, good. I am able to check that my math works. We probably did it all right. So here is our parallel circuit. And again, the things you want to remember. The voltage is always the same in the parallel circuit because we're measuring the same thing if we measure here, here, or here. Whereas the current is the thing that adds together. So whatever current's coming out of the battery has to be the same as whatever went down through R1 plus whatever went down through R2. And then we've got our Ohm's law with the different forms that we can use. And then you can use this if you want. You might have to for some problems. And that, I think, is all we need to know about parallel circuits. So, there we go. Good job.